So far, we've considered a loop in a external magnetic field and how a changing external magnetic field causes a changing flux through the loop, which induces a current in the loop. But what if there is no external field? What if there's just the loop with its own power supply? If the switch here is open, then there's no current flowing. There's no magnetic field around, so there's no magnetic flux through that loop. But if you close that switch, then current's going to start to flow. But that has to take some time. We can't go from zero current to non-zero current instantly. So our current has to increase. It's got to ramp up. And as soon as it does, as soon as current starts to flow, that current is going to be generating its own magnetic field. And from our knowledge of electromagnets, we know that that field will be pointing into the page inside the loop and out of the page outside the loop. So as this current grows from zero to its final value, this will happen very quickly, but not instantly, this magnetic field will be increasing in strength. And so we go from a situation where there's zero magnetic flux to non-zero magnetic flux through the open surface bounded by our loop. That's a changing magnetic flux due to the loop's own current. And if there's a changing magnetic flux through that loop, even if it's due to its own current, that should induce some kind of response that calls upon the electromagnetic inertia of the system to respond in some way. So let's apply our modified Kirchhoff loop law, which we call Faraday's law, to this scenario. So here's our loop, a power supply and a resistor, and that's it. And if we consider a Faradian loop that goes all the way around, that sort of just lies right on top of our wire, then the delta V all the way around that closed loop is 0. This term can be expressed as the sum of our EMF from the power supply here, and then minus IR through our resistor right there, Ohm's law. So that term becomes these two terms, but then there is this, our Faraday term. A changing magnetic flux through our loop it's going to affect our current. There is no external field here, so that changing magnetic flux through the loop is just due to the current itself. So this term, which we recognize has the units and dimensions of a voltage, this term we're going to consider the self-induced EMF, or the back EMF. Here's our back EMF right here, minus the rate of change of the magnetic flux through that loop due to the loop's own current. Okay, so if our self-induced EMF, our back EMF, is due to the changing flux, magnetic flux through the loop due to the loop's own current, we can refer back to the Biot-Savart law and note that the magnetic field here that the loop is creating is going to be proportional to the current in that loop. This law here implies that the total magnetic field we get at any given point will be proportional to the current flowing through that loop. And since the magnetic flux is defined this way, the rate of change of magnetic flux we see will be proportional to the rate of change of the B field, which will be proportional to the rate of change of the current. So the structure of this equation and this definition implies that the rate of change of magnetic flux, our self-induced EMF here, should be proportional to the rate of change of the current in our loop. So based on that argument, I'm claiming that we can write this self-induced EMF as being proportional to the rate of change of the current I. So let's go ahead and make this an equality by putting a proportionality constant in here. And we'll say that our back EMF, our self-induced EMF, will be equal to the opposite of this proportionality constant that I'm defining here times di dt. We're calling this proportionality constant the inductance of the loop. Inductance is a measure of the electromagnetic inertia of the system. Something we've been talking about for quite a while, but now we're actually going to be able to define and measure this property, define the electromagnetic inertia. This is how we quantify that idea with inductance. It's an L, short for Lenz, as in Lenz's law, named for that same fellow, Emil Heinrich Lenz. He was a Russian. The unit for inductance, the SI unit, is the Henry, capital H, named for an American physicist, Henry. And we'll discuss inductance more in the future, how to sort of compute inductance for some system, how to find an expression for the inductance. But for now, let's just let it be this proportionality constant here. So here's our self-induced EMF. And let's imagine the effect that this is going to have on our system here. So close that switch, let this current increase. We're going to be getting an increasing magnetic flux into the page. Well, the system should respond by trying to keep the flux what it was, namely 0. So if we're getting increasing flux into the page, the system should respond by trying to put flux out of the page. We would get flux out of the page if we had a clockwise current. So what we get is an effect as if we had some other EMF over here. This is our back EMF, the self-induced EMF, pointing that way, trying to drive a current clockwise. A clockwise current would be adding flux out of the page inside here, into the page out here, trying to oppose or cancel out that increasing inward flux from this current. Okay, now our net current is going to be going counterclockwise here. This self-induced EMF, this back EMF right here, think of it as a battery that's not as strong as this battery here. This EMF will be less than this one. So we're still going to get current clockwise, but the current won't be as strong clockwise as it would be without the presence of this flux-preserving self-induced EMF, this back EMF right here. Okay, looking at our equation here, if di dt is positive, if our current is positive, clockwise, and increasing, then the EMF is the opposite of that. So that opposite sign indicates that this self-induced EMF, this back EMF here, would be trying to drive a current opposite the current that we actually have. So that's the meaning of this sign here. Our self-induced EMF is opposite the rate of change of our current. Okay, let's consider now this inertia as being something that doesn't just oppose current, but something that opposes a change in current. That's key. So here's our next scenario. Suppose we've got a circuit like this, some wire loop with a battery driving a current this way, and there's a little switch here which can switch between branches. This branch with our battery and this branch without a battery. I suppose this circuit has been on for a long time, so there's a steady current flowing around like this, creating a steady magnetic field in this region. There's our B field, the X's, and the dots right there. Okay, so this has been running for a long time, steady current, steady state flow. Then suppose we shut the circuit off. We flip the switch from there to there. So by flipping that switch, we're taking the battery out of our loop here, and we know that should turn the current off. But it can't turn off instantly. It's going to go from this non-zero value eventually to 0, but over time. So as that current winds down, as it reduces, this magnetic field that it's generating is going to be weakening as well. So we have a flux that was initially into the page, but that flux is going to be decreasing over time, over that very short time as the current is turning off. So a changing flux into the page should be opposed by the inertia of this system. So here a short time later, we've got a weaker current. The current is dying, it's going to 0, so we've got a weaker magnetic field. The system should respond by trying to replace the flux into the page that we're losing. So it should respond as if there was another power supply. This is our back EMF, our self-induced EMF here, trying to drive additional current clockwise to replace the current that we were losing here, trying to add additional magnetic field into the page to replace that flux into the page that we were losing. So here in this case, let's check the equation. di dt is negative since our current was this way, but it's decreasing. So if di dt is negative, then this negative times that negative gives us positive. That's the sense in which this self-induced EMF is pointing in the sort of positive current direction, trying to keep the current going, trying to maintain the current. So between the two examples, we've seen our self-induced EMF oppose the current, trying to stop a growing current from growing. And here we're seeing a self-induced EMF do the opposite, trying to keep a diminishing current from diminishing, trying to maintain it as it was. So in either case, our back EMF, our self-induced EMF, is an effect of the system that tries to keep the current at whatever it was. So let's make an analogy here to the types of inertia we've discussed in this course. We've really mentioned three so far. Mass, the first one, was this property of an object that opposes acceleration, that tries to keep the velocity of an object constant. Mass is a measure of that inertia, that resistance to a change in velocity. For a rigid body that rotates, it has a rotational inertia, or a moment of inertia, which opposes angular acceleration. It tries to keep the angular velocity, omega, of your rotating object constant. And now here we have inductance, L. Some property of a circuit here that opposes a change in the current through that circuit. A property that tries to keep that current constant. These three forms of inertia all oppose these rates of change. I will conclude here by considering what kind of system has a lot of electromagnetic inertia. If we're trying to quantify inductance now, then we need to be able to imagine a system with a big inductance and a small inductance, a large inertia and a small electromagnetic inertia. So a system with a lot of inertia is going to turn out to be a coil, a solenoid. So I've got a picture here of a battery and a wire wrapped into a coil and some resistance over here. I've kind of blown up the coil so we see its coils sort of spread out. We can see it easily. Normally a solenoid would have many, many turns, like hundreds of turns. This is an N equals 4 turn coil here. A solenoid in most practical applications would have N equals several hundred. All right, but for clarity, I've just shown 4 turns in this case. Imagine a circular coil with a radius, little r. If you've got current going this way through our coil, then it's going to be generating a magnetic field, a uniform magnetic field on the inside of our solenoid pointing down in that direction. Okay, so a change to this current will cause a change to this magnetic field here that the current is generating. Now for our coil, the magnetic field is uniform everywhere here on the inside, and it passes through a succession of areas enclosed by each turn of the loop. So here, looking straight down the coil, in green here, I've got sort of the cross-sectional area of one of the turns enclosed. So the cross-sectional area enclosed by one turn of the loop. So there's a self-induced EMF for each turn of the loop, since each turn is enclosing some area that we have flux passing through. So minus d phi b dt through one turn would be equal to the opposite of the rate of change of our magnetic field, which we know is due to the rate of change of the current here, times the area enclosed by one turn. So that would be like the cross-sectional area of our solenoid, of our cylindrical solenoid here, pi r squared. So this is the area we'd be talking about, that green area there that I've indicated here and here and here and here. The total self-induced EMF of the whole coil, however, will be the self-induced EMF of one turn times the number of turns that are present. So N, the number of turns, times that. So we get this expression, which we'll be using for the self-induced EMF of a coil. And we see why this can be a large effect, because N can be a large number. You take whatever self-induced EMF we would get from one turn and multiply it by several hundred or several thousand turns. So a coil like this can potentially have a huge amount of electromagnetic inertia, which we'll be studying further.